Neal, go ahead, introduce yourself, and
Yeah.
we're going to switch topics, I see.
Yeah, a little bit. So Neal Woodbury, Arizona State University, and the last two talks were great, or last two quick talks were great introductions for what I'm going to talk about, because I'm very interested in this whole issue of bias and what it is that essentially evolutionary or semi-evolutionary landscapes look like. And also, just like Armada, a few years ago, it wasn't my graduate student, it was my son who came home for Christmas. I was showing off the great work that I was doing, and he said, well, actually, and he sat down in 2 days and redid it all with machine learning with far higher accuracy. It was also both depressing and very interesting, and sent me off a new direction.
Now?
What?
And where does he live now?
He now lives...
That was a joke.
Well, he's now doing machine learning at a biotech company in California, probably quickly making much more money than I will ever make. Anyway, okay, so I have been inspired by this system. This is a B-cell system. It is like evolution, except it works a heck of a lot faster. And the interesting thing about the B-cell system is that in a very short period of time, what it does is it identifies something entirely new, and so these B cells have to bind to weak, non-specific things, and then very rapidly find a strong, specific binding capability. And so they've only got a few days to do that, and of course I think most of you are aware of how they do that. They go inside this germinal cell, and they crank out they undergo essentially a selection process for proliferation over a period of time. So the interesting thing about that is that you can't really pull this off very easily without having a relatively smooth kind of topology associated with the amino acid space that they're searching, right? Because otherwise they wouldn't get to the top peak with an ascent type approach. Because they start with an extremely sparse sampling of that space, and then they have to basically find their way to the top. So we use a very, very simple, we use a very, very simple system. Actually, I don't even have a picture of it here. A very, very simple system for mimicking the same kind of thing. In our case, what it is it's an array of peptides. These peptides are 10 plus or minus 3 amino acids long. We've got maybe 100,000 of them on the array, and we bind different things to them. Now, a lot of the time when I'm binding to them are antibodies, because I'm interested in how antibodies interact with this space. And when we try to understand how it is that a unbiased look at that system will allow us to, what kinds of information we can get out of that using machine learning. So you get binding values for 100,000 or a million different peptide sequences, and you put that into machine learning, and you ask, how well does that tell you about the other 10 to the 12th, 10 to the 13th sequences that are out there? And it's very interesting, and I'll just give you one example. If I use this with a monoclonal antibody, now this is a model system. I'm using a monoclonal antibody for a linear sequence, so it's specifically for a linear sequence. If I use a model system like that, I can bind the antibody to that sequence, and if I let the machine learning do whatever it wants, it does a great job of then, even though I don't tell it anything about the cognate, it does a very great job of identifying the cognate sequence for that monoclonal antibody. However, if I go and try to be a chemist, and I try to tell it what the properties of all the amino acids are as the input, rather than just giving a letter for the amino acids and letting it use some one-hot representation for that, it can't do that job at all. So it actually confuses the heck out of it to give it the chemistry. So I think that it's all very interesting to see what the biases are in these systems and how it tells what's going. So that's the kind of thing I do, and we apply it to a lot of disease-based systems and whatnot.
Okay, great. Any quick questions about? Yeah, go ahead. Where's the? Oh.
All right, I had a quick question about the B cells. When you say that they're kind of like sparsely sampled, so each individual B cell, it has its own unique sampling of kind of that sparse?
Well, no, so you've got about 1 billion B cells, and they are sampling the system. And what happens is that the ones that show weak binding, what will happen is that there's actually a region in which this takes place. They will be selected more and more strongly for binding, and so you essentially the target goes down and down in concentration, and so they have to get better and better and better at binding to that. So that's how your system generates antibodies in a short period of time.
But you're leaving out the process whereby the diversity is generated, which is the mutation process.
Right.
So you
Inside
should
the
mention,
B cells,
yeah.
yes.
I mean, it's not
They're
just that
constant.
you have.
As they're
the same
proliferating.
sequence of B cells, you actually mutate new ones to try.
Right.
Yeah,
Yeah.
it's mutation selection.
Right.
Thanks.
Yeah, quickly, yeah, go ahead. Take the mic from behind you.
Yeah, another very naive question, but how convergent is this? Like, if I take two different people exposed to the same disease, do they look similar?
Yeah, that's a really good question. It depends on the disease, and we could have a much longer conversation about that. If it's a very small virus, you get very convergent things taking place. If it is even a larger virus like coronavirus, then you start to get much more divergent things taking place, and so it really just depends on that sort of situation.
Thanks.
Okay, well, thank you. Okay,